Today's webinar is part of our variation series, which is based on articles written for our quarterly publication. If you haven't had a chance to read the publication, it can be found on the homepage of the U.S. CLIVR website. The spring 2017 edition, which we're hearing about today, is called A Case for Observing the Deep Ocean. And with that, I'd like to welcome you and introduce you to our guest editor for the edition and our host for today, Rynellis Perez.
Thank you all for attending. Oh, thank you. Hi all, it's me, Rynellis. Thank you all for attending the U.S. CLIVR webinar focused on observing the deep oceans. As we all know, the deep oceans play a crucial role in the Earth's climate, primarily through property redistribution via the large-scale overturning circulation, as well as serving as a massive reservoir for heat and carbon storage. Although the deep ocean has long been perceived as slowly changing, the limited observations from the last few decades show pronounced changes in deep water mass properties, and these changes suggest that the deep ocean has already begun storing excess heat and carbon from the atmosphere and is thus playing an important role in the Earth's energy imbalance and carbon cycle. For all of those reasons and more, expanding the global ocean observing system into the deep ocean is of high societal importance. The webinars that you're about to hear today highlight existing state-of-the-art methods for measuring the deep ocean, and we'll hear some of the scientific insights that we've already gained from these observations, as well as new methodologies and technological advancements to expand the network of deep observations. Today you'll be hearing presentations from Gregory Johnson at NOAA PMEL, Lynne Talley at Scripps Institution of Oceanography, Felix Landerer from NASA JPL, and Nathalie Zilberman from Scripps Institute of Oceanography, and Charlie Eriksen from the University of Washington. I hope you enjoy these as much as I know I'm going to. Thank you.
Great, thanks, Rynellis. Greg, why don't you kick us off?
All right, very good. Let's see. So the title, I submitted an article for the CLIVR variations on roles of the deep ocean and climate. This was written with Mike Winton. Any errors today are solely my own. And I'm going to focus actually mostly on the heat and hope that others take up the carbon today. So we'll start out with a slide on Earth's energy imbalance, then a few slides on deep ocean circulation, water masses and timescales, then introduce the observed deep ocean warming that we are seeing over the last few decades, and then talk about deep ocean warming in climate models. So if we take a look at this slide from the 2013 Intergovernmental Panel on Climate Change report of Working Group 1, we look at this as a slide of global energy flows. It's very complicated, but I'd really just like to focus on the top and the bottom of the slide. So if we look at the top of the slide, we have about 340 watts per meter squared of incoming solar radiation at the top of the atmosphere. That's averaged over the entire surface area of the Earth. About 100 of that is reflected, either off clouds or off places with fairly reflective places on the Earth's surface. And then 239 watts per meter squared are re-radiated to space as long-wave outgoing radiation, and that's the upgoing arrow on the right here. If you look at those three numbers, you'll notice they don't quite add up to zero. And there's an imbalance, which is on the bottom, circled in red on the bottom left of the slide here, and that's about 0.6 of a watt per meter squared. And the IPCC estimated it, the uncertainty is somewhere between 0.2 and 1 watts per meter squared. And this slide was made by atmospheric scientists. It has the imbalance going into the cornfields. It doesn't actually go into the cornfields, though. It goes into the oceans. And so the next slide looks at the thermal energy storage. And because that's the big difference of small numbers at the top of the atmosphere, it's easier actually and more accurate to look at changes in energy inventory in parts of the climate system. And so the slide on the right, the axis goes from 1970 through 2011, so it's a little over 40 years of energy storage, accumulated energy storage in the Earth's climate system. And the y-axis is in zettajoules, 10 to the 21st joules, so these are huge amounts of energy. The light blue is the accumulated The light blue wedge here is the accumulated amount of energy in the upper 700 meters of the ocean. The dark blue is the accumulated amount in the ocean below 700 meters, so it's from 700 to 6,000 meters. The smaller wedges, the light gray, is about 3%. That goes into melting ice, both on land and sea ice. And then land warming is the orange bar here at about 3% of the 40-year trend. And the atmospheric warming is only about 1%. That's actually the warming and the energy required to increase the moisture content of the air as it warms. So the net trend is about 0.4 of a watt per meter squared. If you look from 1993 to 2010, more recent time period, that trend goes up a little bit to about 0.5 of a watt per meter squared. Probably not statistically significant in the difference because the errors are fairly large. You can see the uncertainties there in the dot dash lines that circle the top of the curve, and those sparser observations make uncertainties larger in time. But we can update this. If we look now at the ocean heat content from 1993 to the present, this is from a article that will come out in the State of the Climate 2016 report. We now look at 5 different groups, estimates of upper ocean heat content from 0 to 700 meter on the top panel. Again, the y-axis is zettajoules. This time we're going through 2017. You can see this steady march. You see the uncertainties on all those curves actually get much smaller as you move into from 2005 to 2015, and that's the effect of Argo really increasing our certainty of the amount of warming in the upper ocean, and that extends down to the bottom panel, which is from 700 to 2,000 meters, the red, green, and orange curves. And again, they are pretty tightly constrained and come together after about 2005. The dark blue wedge in the bottom panel here is the deep ocean warming below 2,000 meters. And that's about 10% of the total ocean heat gain, which is somewhere between about 0.65 and 0.8 watts per meter squared. So this is a small but significant amount and statistically significant of heat gain. You'll notice that that ends in 2010, and that's because we are limited to decadal surveys, as I think Lynne Talley will hint at later. And then deep Argo going below 2,000 meters will hopefully allow us to monitor deep ocean heat content in more real time. So what would change how could the heat of the abyssal ocean change is a question I often get. And this is a slide that's modified from a paper by Lynne Talley in Oceanography of the meridional overturning circulation. In the south, on the left side here, you have Antarctic bottom water sinking. That flows north in the Indian Ocean and the Atlantic Ocean and the Pacific Ocean, all 3 oceans. And it's formed at a rate of about roughly 15 sphere drips, about 15 million cubic meters per second. The North Atlantic deep water on the right-hand side of the slide is cooled and sinks down to the deep depths, the bottom in the North Atlantic, but deep everywhere else, overlies the Antarctic bottom water, and there's a fairly complicated loop that I won't get into. But basically, the take-home here is that the bottom waters are ventilated by Antarctic bottom water from the south, the deep waters by North Atlantic deep water sinking in the north, and changes in formation rates and water properties could either of those or both can warm the deep ocean. So if we look at the Antarctic bottom water and North Atlantic deep water concentrations, and this is from some work that I published in JGR in 2008 actually, let's look at the upper right-hand panel. You can see this is fraction of North Atlantic deep water. The y-axis goes from Antarctica on the left side to, the x-axis, Antarctica on the left side to the high latitude Arctic on the right. It goes from the surface down to 6,000 meters. And the darkest blue is above 90% North Atlantic deep water concentration, zonal averages in the Atlantic. The white is less than 10%. So you can see this North Atlantic deep water, a high concentration spreading south at mid depths. If you go on the upper left, now I've flipped the axis so that Antarctica is in the center. So we're going from Antarctica on the right to the Arctic on the left. And you can see a little bit of a remnant of North Atlantic deep water in the Indo-Pacific. Concentrations above 20% say is only averaged. This blob here on the right that's going from 3,000 to 1,000 meters, but then somewhere between 10 and 20% in the rest of the deep ocean. If we go to the lower panels on the left, we see that, in fact, what's filling the deep ocean in the Indo-Pacific is Antarctic bottom water, concentrations as high as 80, 70, 60% below 3,000 meters. If you look on the lower right panel, you can see that Antarctic bottom water very strong in the wet El Gyre here of the Southern Ocean, in this 90%, exceeding 90% down there, but also filling the western basin of the South Atlantic. In fact, having equal to or higher concentrations in the western basin. This is the zonal average over both the western and eastern basins. Another thing to note is that the Antarctic bottom water volume is about twice that of North Atlantic deep water, and if we divide the volumetric amount of Antarctic bottom water by its formation rate, you get a filling time of about a millennium. For North Atlantic deep water, the filling time is about 6 centuries. So that's a time scale for, in fact, for climate adjustment, for the ocean to, the deep ocean to adjust to atmospheric temperatures, changes in atmospheric conditions, CO2 temperatures. So over the last couple decades, as Renellis alluded to, we have seen deep ocean warming. This top left panel is after a study by Perkey and Johnson, 2010. It shows warming rate below 4,000 meters averaged in deep basins, which are outlined by the 4,000 meter contours here in thin black lines. It's averaged, and it's a warming rate from between the World Ocean Circulation Experiment in the 90s and the CLIVAR CO2 surveys, the first CLIVAR CO2 survey, which ended around 2010. And the warming is strongest in the bottom waters around the Antarctic, but it spreads all the way up into the North Pacific, into the eastern basins of the Indian Ocean, up the western basin of the Atlantic, and the stippled areas, however, are places where we don't have enough data to show that this warming is statistically significant at 95% confidence. So it is these sparse decadal ship surveys, and you can see the repeat lines in the solid, thick black lines. Those are the repeats that were done first in the 1990s and then again in the 2000s. That allows us to reveal deep ocean warming, but it's really a qualitative assessment. The uncertainties are fairly large, and we only get a refresh on sort of decadal timescales. To show what that looks like in the vertical, the bottom right shows an example from the South Atlantic. And so we're going from the Scotia Sea, Antarctica on the left, to up to the equator on the right. What's contoured in colors is the warming trend from 1989 to 2014. There were 3 occupations of this section, 1989, 2005, and then under Go Ship in 2014. The rate of warming exceeds it's average about 3 millidegrees C a year here in the Brazil Basin, which is consistent with the colors in the upper left panel. They're not the color scale is not the same, but the rates are about the same, about 3 millidegrees C a year. And you can see warming in the deepest, coldest waters here as well in the rest of the basin. There's a strong thermal gradient. What's overlaid in thicker black contours are the mean potential isotherms contoured at 0.2 degrees C from 4 degrees C up at the top at 1,000 meters down to 0 and below in the southern part of the section. There's a strong thermal gradient between the Antarctic bottom water, this thick, relatively homogeneous temperature water in the bottom of these basins, and the North Atlantic deep water, which is this relatively homogeneous region here. You can see here that in contrast to the Antarctic bottom water, in the western South Atlantic, the North Atlantic deep water is not showing much warming. It oscillates around 0, and these are mesoscale eddies that even persist when you average the trend over 3 sections. So as we can see this deep ocean warming in models. So this is a paper by Frank Bryan and colleagues showing results from 2 runs of doubled CO2, and on the left is a standard resolution climate model labeled LR. This is temperature change for the 20 years after doubled CO2 compared to the beginning of the run when we have pre-industrial conditions. And then the right-hand side is a high-resolution model. And there is a difference here. The low-resolution model forms Antarctic bottom water by deep ocean convection. It convects mostly to mid-depth, and you can see that the reduction of that convection in the low-resolution model under doubled CO2 has resulted in this warming that reaches down to mid-depth. In the right-hand side, the high-resolution model actually forms Antarctic bottom water versus by formation of dense water on the shelves and plumes of that water which then descend to the ocean bottom. And that's what we observe in the modern ocean. And you can see this bottom intensified warming, so warming throughout the Southern Ocean and then a bottom intensified warming that extends northward. And that's reminiscent of the slide that I just showed you in the South Atlantic. So are we seeing this bottom intensified warming already? Maybe we are. If we look at the roles, just step back and think about the roles of the ocean in climate. This is 4 different CO2 scenarios. Just concentrate on the green lines here. So this is on the upper right panel is CO2 concentration from 1900 through 2200. If we have a scenario where we stabilize at the end of this century and then hold the CO2 constant with a couple of different scenarios. If you look at the global average surface temperature on the bottom right panel, you can see that even after you stabilize in the green, especially in the CCSM, which is the high sensitivity model, you see that the surface temperature continues to warm, and that's the response of the upper ocean to thermal changes. So that's the upper ocean coming into equilibrium. It's sort of in the last few decades of this century, it kind of levels out, and the upper ocean has sort of a decadal time scale. But if we look now in contrast at sea level, you can see that the sea level just continues to rocket up in all these scenarios, the green and the blue curves here. And that's the large heat capacity and long ventilation time scale of the deep ocean, which is important. Of course, ice melt is important too, but in this model, I'm not even sure that ice melt is included. And so this is really just the equilibration time of the deep ocean. Just about done here. So we see in the IPCC models, this is model temperature change, multi-model mean of climate models from 2090, so a 20-year average at the end of this current century compared to 1995, again a 20-year average from 1985 to 2005. And you can see, again, this deep warming in the south from the Antarctic that's penetrating deep over time. And that's just a reminder that while the Antarctic bottom water, the deep water warming is only 10% of the total of the ocean heat uptake now, in the future it's going to be an increasing percentage. And it's going to be especially strong around Antarctica, but will penetrate throughout the global oceans. And then the right panel is just looking at present model deep ocean conditions and how they're correlated with future warming. So if you just look at ocean temperatures now of a whole bunch of models, the models that tend to be cold in the middle of the deep ocean and warm around Antarctica tend to predict a warmer future. So understanding how the deep ocean, what the deep ocean characteristics are and how they change with time is actually quite important with understanding how both sea level is going to rise and the Earth's surface is going to warm. And so with that, I think I've gone a tiny bit over, so I'm going to just leave these slides up and pass it to the next speaker. Thank you.
Thank you, Greg. Very nice presentation. We will take a moment if there are any questions for Greg. Just as a reminder, you can type them into the chat feature, which we all can see, or feel free to raise your hand. Okay, I don't see anything has come in so far, but we will have hopefully some time at the end for questions. So I'd like to turn this over to our next presenter, and that would be Lynne Talley. Lynne, go ahead.
Hi, can you hear me?
You sound great.
All right, cell phone to mouse. Okay, so I'm going to follow on a great introduction from Greg to tell you about the way that we've been measuring the deep ocean over these many, many decades. And we'll continue to as basically the background reference sections with highest quality. So this is a contribution from Ghost Ship. And I'll actually, can I advance these slides? Yes, I can advance them somehow. How does that work? Yes, good. The contribution of Clivar variations is by myself and Greg Johnson, Sarah Perkey, Dick Feely, and Rick Lanikoff. You'll recognize that Dick and Rick are a carbon group, heads of major carbon groups. The second slide shows the two publications. One is the Clivar variations above, and below I'm highlighting an annual review of marine science, which was a summary review of what we found in Ghost Ship from the first decade of the global repeat hydrography in the period past WOF. And this is an international Ghost Ship contribution, but it was actually started as a U.S. Clivar white paper, thanks to the U.S. Clivar office. So first of all, if you're not familiar with what Ghost Ship is, this is a successor to WOF. And in the first decade, it was called Clivar CO2 repeat hydrography. It's a 5 to 10 year repeat of key sections across ocean basins, top to bottom. Bottom is important. We go within 5 or 10 meters of the bottom. So if you doubt that we're looking at bottom water, we are doing it. We go coast to coast. We have nominally 30 nautical mile separation, but often it's bigger, a little bit bigger. Most important thing is that our measurements are very accurate, and we have a large number of required parameters, which are both physical and biogeochemical, and we also have shipboard measurements. I can advance here. This is the International Ghost Ship Decadal Survey. This is from the Ghost Ship website, international1ghostship.org. See lots of crisscrossing lines, and there's different categories that I don't have time to go into. This is the U.S. contribution to the Ghost Ship array, and we occupy roughly 2 sections a year. And this is split between NSF and NOAA funding. And I can go on. We go to sea. I've got some pictures. On the left, we do, this is our big workhorse CTD rosette. A bunch of people with nice NSF vests on there doing sampling after it's come up. On the right is the future. Part of the future is we're going to be probably taking on a lot more biologically relevant measurements. There's a SCORE working group that just made a recommendation for pretty comprehensive additions to Ghost Ship with modern instrumentation. And this is just a, a numbing table, but of all of the measurements that were made on P16 South, one of these sections that I happened to lead 2 years ago. In blue are the ones that are the basic required program. They're called level 1. In red are ancillary programs that happen to be on that cruise. Those shift all the time. The blue ones are on every cruise. You can see that almost half of our programs are ancillary and very important. So a bunch of those are actually these biological measurements. Some are mixing measurements that have been, we're doing an experimental phase on every cruise for a few years. So there's a lot of stuff going on the ship besides just measuring the deep temperature. Very important is that we're also measuring, in addition to the physical parameters, the carbon system. This is something you can't get at yet from autonomous floats going to the bottom. We are in the beginning stages of being able to do that with biogeochemical Argo in the upper ocean. So this is just another nice picture. On the left, the CTD lab. On the right, one of the chemical labs on the ship. And we make tons and tons of measurements, and illustrated by temperature on the left and pH on the right. This happens to be in the South Pacific, Ross Sea on the left, Tahiti on the right. So what are we after? Relevant to the deep ocean. Greg has already introduced us to heat, so I'll go over it very quickly and move on to carbon, basically. He showed you this slide already. This is an illustration from the IPCC AR5 of the global energy. The blues are the ocean, light blue is the upper ocean, dark blue is the deep ocean. The little slivers down below are everything else. So as Greg is fond of saying, global warming is ocean warming, and about 90% of the heat is going into the ocean. And he showed you the estimates. The deep ocean is about 10% of the ocean's warming, 10% of that 90%. So we need to measure it. And he's also shown this, although he didn't show the top plot. The top one is the upper ocean warming. And you can see it's pretty much red everywhere. There's places where it's redder than other reds, and it's splotchy. That's because this is a database that goes back to the 50s and then ends with Argo. So we're lucky to be able to map it, but it's basically red with some noise. At the bottom is what he showed you for the deep ocean, which is not overall red everywhere. It's very much intensified in the south, and that's been a very interesting area of research and thinking of why the Southern Ocean is, oh yeah, I can use that arrow thing, huh? Thank you. There, I can do it. In the last 5 to 10 years, well, since 2010, since the Perky and Johnson paper, for 5 years. These maps are made entirely from these data on these lines. Guess what those are? Those are WOS in the 90s and Ghost Ship, Clivar repeat hydrography and Ghost Ship now. And that is our way of getting at basin-wide inventories of heat and other properties. This is an update to the Perky and Johnson. This is by Des Broyers et al. Sarah Perky was a lead on this one. This is showing the newest results for the abyssal ocean. It includes the deep layer and the abyssal layer. It's holding up that the Southern Ocean is warming more than other places, and they have some very nice discussion in the paper about why the North Atlantic actually cooled in that period. The North Atlantic has a natural variability of the North Atlantic Oscillation up and down, and the Southern Ocean has sort of variability in the sense of forming less bottom water, so it's getting warmer. Onward. This is just one brief slide about salt. There actually aren't too many papers showing all of the, all the changes in the deep fresh water. This is a dramatic change around Antarctica, also from Perky and Johnson. And on the right is just a section showing raw sea bottom water changes. So salinity is changing, especially close to the sources, and it's very interesting to understand it. If you want to understand the freshwater balance of the globe, top to bottom, you've got to do top to bottom of the ocean, and you've got to use, at this point, Ghost Ship measurements coupled with WOS and then earlier hydrography to look at how the freshwater is changing. I'm going to move straight on into carbon and ventilation timescales. These are all written up very briefly in that Clivar variations paper, so have a look. This is a graph of the carbon, the anthropogenic carbon changes in the Earth system. This is also from the IPCC. It's from the carbon chapter. The upper part is what's going in anthropogenically, and the bottom part is where it's ending up. And so this dark blue sliver down here is where the ocean is, atmosphere and land. So you can see this is actually pretty different from the heat. In the heat, 90% of it's going into the ocean. For carbon, it's pretty equally split between the ocean, atmosphere, and land. So that's kind of interesting. We're looking at a different kind of signal for carbon, although how it gets in, where it gets in, is kind of similar to heat. So understanding the whole global overturning circulation is very important for getting this sliver right. And let's see, how do I advance? These are some measurements. I'm just going to show you some gee-whiz, interesting pictures. This is from Wanenkoff et al. In JGR 2010. Rick has led a bunch of really important papers, and Rick and Dick Feely, showing our measurements of changes in carbon. So this is the Atlantic. This is a meridional section down the middle of the Atlantic. First occupation was 1989. I guess I got to be on parts of that. Mike McCartney proposed this thing before WOS. And then it's been occupied a couple times since then. They're comparing it to the 2005. And if you read their paper, you can figure out exactly how they went into calculating the anthropogenic carbon. It's not dyed with anything. You're having to use carbon measurements and other measurements of ventilation timescales, such as CFCs, to figure out what portion of the carbon is anthropogenic. But it's a lot of work, and this is a very credible answer from Antarctica up to Iceland. You can see the penetration of the anthropogenic carbon deep into the Atlantic. And they're showing isopycnal surfaces. I find this much more visceral, visual graphic of the ventilation. This is the chlorofluorocarbons, which of course are man-made only, and they have a very specific time history in the atmosphere. If you combine different CFCs together, you can get ages. And just showing the CFC shows you where our influence goes in the deep ocean. This is the same section down the middle of the Atlantic, Antarctica left, equator, Iceland to the right. This is the CFC section in basically the WOS section at the end of the 1980s. Where there's color is where there are man-made CFCs in the water column. So that's pretty cool. There's the Antarctic bottom water region. Here's the Weddell area. This is the North Atlantic deep water. There's the thermocline. There's nothing in between in 1988-89. That means there was no water that was older than about 40 years there. By 2003 and 5, the circulation started filling in. Now we're 50 years down the road. Now you're seeing 50-year-old water or 50, 60-year-old water. You can see these edges filling in as the water gets successively into that age range. And here comes the equatorial flow in from the western boundary. That's very nice. You can see the North Atlantic deep water components coming across the equator. And you're filling in at the bottom. So these CFCs are a nice way of showing that we do have an anthropogenic mark in the ocean. The carbon measurements, there's a lot of carbon out there, and figuring out which part is anthropogenic does take a lot of calculations. So it's nice to see it from the CFCs. This is the last of the, not almost the last of the graphs. Actually, I'm going to follow up on the right panels because they're beautiful color. This is from Monica Ryan's group. This is showing the Denmark Strait overflow water layer. They also have maps for layers above that, but since this issue of Clyde variations is on deep ocean, I love this plot. This shows where there are CFCs, and that looking at the time scales, this is measured in years, of the water masses in that, of the waters in that water mass, the Denmark Strait overflow water. And you can see it penetrating all the way down to 20 south. And this gives you a gauge of how long does it take North Atlantic deep water, new stuff, to get all the way south down into the South Atlantic, and then you can sort of, so that's got to be 50 years or so. Another double that down to Antarctica. So about 100 to almost 200-year time scale to get this to outcrop in the Antarctic. That's an important part of the overturning circulation. And then they've looked at the fractions of the young parts of this that are deep, the Denmark Strait overflow water. In the left, these are really important results. That they're just a black and white graph, and we are so used to color. They're gorgeous. This is the inventory, basically, of CFC in along that A16 section down the middle of the Atlantic. Upper one is focused on CFCs and the anthropogenic carbon in the model. They're using an NCAR-CESM model. And the lower one shows measurements of dissolved inorganic carbon and the changes. Basically, the change can be attributed to being anthropogenic. And then they calculate it two different ways, one by actually measuring the DIC and the other by using PCO2 measurements to back out DIC. And so what they're showing averaged over the whole A16 section, the whole latitude range, is basically at the top one you see CFCs penetrating to 4,000 on average. And the delta DIC, that's the anthropogenic carbon, also down to 4,000, regardless of how you calculate it. This is from Wanenkoff et al. DSR 2013. So there are inventories of anthropogenic carbon. This is from Kadiwala et al. Many people contributing to this. This is a top to bottom inventory of anthropogenic carbon. It's based on these measurements and a way of interpolating them. And it's a very important map. And you don't get this map with anything but a ghost ship WOS type measurements. So you can spend a lot of time analyzing. Well, let's look at it. There's a band of high anthropogenic CO2 here along the northern side of the Antarctic circumpolar current, basically related to subduction into the gyres from the edge of the current. And then, of course, a very big bullseye in the North Atlantic where it's very well ventilated. There's some other little interesting ones there, Japan Sea. And you can start backing out the circulation, input of carbon, and the storage where it's happening. And the Arctic has quite a lot. So that's what we're doing in terms of climate change from ghost ship WOS sections. What's important is that we're measuring repeat sections decadally, so that we're not, not biased or by being in a different location. There's a lot of concern about our not having snapshots, but the way we argue with that is to say that we're doing basin integrals. So if you see a signal that extends over, half of your section, it's probably not just an eddy that shifted something over. But you do have to be careful about that. Did the ACC front shift? Is that why you're getting a change? But is that change maybe with what you're looking for? So we do carefully interpret our measurements, these decadal measurements, in terms of what could be the time dependence that may be aliasing the results. But basically, when you're looking at large area integrals of changes, you're getting the correct information. So what we're getting from Ghost Ship is the deep ocean heating, deep ocean freshwater changes, and entire ocean carbon changes at this point. We can also get into lots of other things. Oxygen, there's a lot of interest in oxygen minimums, but that's not the deep ocean. Nutrient changes, et cetera. Ghost Ship, as it moves forward, adds more tracers. These are some new ones that have been added. SF6, which goes with the CFCs. Nitrous oxide has gotten to be straightforward to measure and is interesting, very interesting to biologists. And we're doing mixing measurements now too, mixing related measurements. This is looking at temperature microstructure from this special very fast response thermistor added to the CTD package on stalks up above it. And so Jonathan Nash, Jim Moom, and Jen McKinnon are backing out sort of diapicnal diffusivity, dissipation diffusivity from these measurements, and they're doing it on all of the U.S. sections now. And as you all know, if you're following physical oceanography these days, that's a really important thing to do. We really want to know where the mixing's happening. Where's the water? Where's stuff diffusing down? Where is it mixing up? How's it coming? How's it moving around? So I just want to finish off by saying that where we are, this is a very important program to maintain. As we move into newer technologies of deep Argo and gliders and so forth, we still need what we call reference accuracy data. This is what we get with Ghost Ship. This is the best calibrated out there. And we're there on site on the ship to ensure that. We do measure to the bottom. We do repeat. And we have lots of biogeochemical variables that are as important to measure for climate change. And we are anticipating an expansion. Our next expansion will be into biological parameters using plankton observing sensor systems. So I think that's it. I will show why we are kind of keen to see autonomous instruments. Here's when the second mate turned the ship a little too fast at the end of a station. Nobody was out there, thank goodness. So thank you.
Thank you, Lynn, for your nice presentation. Are there any brief questions for Lynn? Take just a moment here. All righty, let's move on then to Felix. And Felix, feel free to go ahead and get started.
Yes, hi. Can you hear me okay?
Sound great.
Okay, thanks. Well, thanks everyone for joining this webinar. I want to thank and acknowledge my co-authors, Cecilia here, who coordinated this write-up for the newsletter, Don Chambers, University of South Florida, Dennis Volkov at Miami, and William Lovell. So switching the vantage point a little bit from actually measurements in the deep ocean to a near Earth orbit, and that might be a little bit of an unusual perspective for measuring things happening in the deep ocean. So I'm just going to spend, let's see, how does this, okay, here, one slide on how GRACE actually works. So GRACE stands for the Gravity Recovery and Climate Experiment. It's a system of two twin satellites. They're identical. They're kind of chasing each other. And what we're doing with these satellites is we're measuring monthly gravity changes over the entire Earth. And we do this by simply tracking between the satellites. So there's a microwave link here that constantly measures distance changes. And those distance changes are directly proportional to the gravity field. So you can imagine, since everything has mass, if mass changes on or near the surface of the Earth, the gravity field changes. So from gravity, we go to mass, and of the ocean, in fact, this is the total column mass at the seafloor, because it's the integrated stacked up mass. And the resolution that we get is about 300 to 300 kilometers for a monthly gravity field. And you can kind of see this here indicated by the tiling. So we call these units here mass concentration fields. And we can measure the gravity changes to within about 10 millimeters water equivalent height. So that's our accuracy that we get here. So in this presentation, I'm just going to take, let's see, does this go forward? Okay, here we go. So in this presentation, I'm just going to show a couple of examples of how GRACE data can help us learn about what's going on in the deep ocean. And here I'm just showing the entire GRACE data record in its entirety. This slide is not meant to see any detail. It's way too small. You can't. I just want to give you a sense of what the GRACE data is. So we've been in orbit since 2002. So every row here is a year. Down here is 2016, and this is the annual cycle, start in January and then all the way through December. So you can see that we have a near complete data record here towards the latter third or so of the data record. These gaps start to appear. That's because our satellite is now, for space standards, ancient. So we have some battery issues where we occasionally need to turn off the instruments. But the point that I want to make here, the takeaway message, is that we get every month a complete global map of these mass changes. And we're not impeded by the presence of sea ice or clouds or anything like that. Our measurement is always complete because the satellites just sense the gravity. If you kind of squint your eyes and just go down one column here, you can see that it's a little more blue, quite a bit more blue down here in the latter part of the record. And if you see here, this is the color scale, the anomaly. So this means there's more mass in the ocean. And what that simply tracks is the increase in sea level due to mass changes. So my first example would just be to highlight some applications we can do with GRACE for the sea level budget. I'll start out with a global view and then show a regional application. And in principle, it's pretty straightforward. It's just the total sea level that we would measure with the altimeter, for example, is comprised of the steric contribution, so the density, and a mass contribution. Density we get from Argo. Of course, that's currently, at least in the global scale, limited to the top 2,000 meters. And the mass field here with GRACE is, like I said, essentially the exchange between the oceans and the continents. So we have a seasonal cycle. We also have a long-term trend. I'll speak to that in a second. This equation, at least, is complete. What's actually missing here is the fact that there is actually a small residual term, which would, in terms of the measurements at least, is from the deep ocean. So that's really what this webinar here is about. So I'll speak to that in a second. So if you bring all these terms onto the left or right side and look at the residual, you could potentially learn something about the deep ocean contribution here. So that's one of the applications that GRACE and altimetry and Argo have been combined to. So here I'm showing a plot contributed by Don Chambers, which shows the so-called global sea level budget. So the black line is what you would measure with an altimeter. It's a global sea level curve. The seasonal variations have been removed. This is over the last decade, so 2005 to 2015 or 14. And the main message here is that if we sum up all our measurements, so the mass and the thermosteric, this is the mass and the thermosteric from Argo, we get here to the orange line, and that matches pretty well with the altimetry. So the takeaway message from the global sea level budget is that the deep ocean contribution to warming, at least as it expresses itself in steric sea level, is relatively small at this point. And that's very consistent with what Greg and Lynne just talked to in the previous two talks. Of course, the steric expansion coefficient is smaller in the deep ocean, so the sensitivity of the global sea level budget is somewhat reduced as you go down deep. This is from a global assessment. We can do this. I keep pressing my keyboard here to advance. Okay, I got it. Okay. We can also do this on a regional scale. And this is from a paper that Dennis published recently, which also does so this is all trends. And the map here shows the difference between the altimeter and GRACE. And if you think about the sea level budget that I showed previously, that would equate to the steric sea level trend. And you can see this prominent signal here in the South Pacific that Lynne also mentioned. And it also actually highlights the transects, P06 and P16 here, going through this box. And if you break it down, the total sea surface height, so the sea level curve in this box here, has a trend. The mass component has not a very significant trend, but it is going upward. And if we do the difference, we get to the steric. Now, if we pair this with Argo, you see that there is actually a widening gap. So if we compute this difference, we would actually infer a deep warming trend of about 1.8 millimeters per year. It is significant within the uncertainties, and that's fully consistent with the transect measurements. Just one point I want to highlight is that the transects, I think they occurred, they're on, as Lynne said, on a decadal time scale. So we had a campaign here, I think 2004, 2005, and then later on in 2015. So the combination from space-based measurements, altimetry, and grades allows us to get a continuous time series. Of course, there are quite a few uncertainties and corrections that we need to make. So I'm not entirely sure that these interannual type variations are real, but this is certainly something that the community should pay attention to and look into. And it also means that, right, if you have your ship campaign in this period or here, you might alias some of this short-term variability into your trend. So then going on to another example of using the vantage point of space for deep ocean studies is using bottom pressure gradients to infer transport. So that's basically just very plain geography. I think for this audience, I don't really need to explain this picture much. This here actually is a cut at 26 North where the rapid area is located, and just depicts conceptually the warm water transport in the upper layers, and then the returning cold transport in the lower North Atlantic deep water layer. And I just want to sort of showcase a proof of concept study that we published late 2015 that essentially shows that we can use GRACE measurements of the bottom pressure gradient across the entire North Atlantic to infer this lower North Atlantic deep water variability. So other examples, for example, Don Chambers has published a lot on the ACC. I don't have time really to show an example. Here I mentioned that at 26 North, the same cutout is where the rapid area is located. Lots of profiling stations here installed. Very valuable record, I think over a decade now, of in situ measurements of and really on a monthly and higher time scales of the entire cross-section transport. So this is really valuable for us to sort of verify our measurements. Here's same. Let me just go to the next slide and skip this. So here I have this cutout again of the bathymetry, and what I wanted to focus on is this lower North Atlantic deep water layer. So that's between 3,000 and 5,000 meters. So in this layer we have a net southward transport of the cold water. And if we take the measurements here at the western boundary from GRACE, we get this upper time series here. So this is bottom pressure. The variations here on the order of 20 millimeters of water height, so really quite small, but measured from space. And then on the eastern boundary, we get this time series. For the transport, you need to take the difference or the cross-spacing gradient, and then integrate and multiply with a few constants, directly get the transport. You see that most of the energy to the variability is contributed by the western boundary. That's very consistent with theory and measurements from rapid. So if we integrate this, we get this time series here, the blue. So this is a purely space-based lower North Atlantic deep water estimate from GRACE, the blue time series, and the in situ estimate from rapid. So there's really no, these two estimates are fully independent, right? So and the agreement is pretty good, 0.7 in the correlation. You see that sometimes we do have some differences, and we're looking into that, what exactly that is and where that comes from. But this is a very nice proof of concept. So what this allows us to do, of course, we're not limited to looking just at 26 North. we can go to any other latitude and essentially do the entire basin. And here I've just plotted a correlation plot. So I've just taken the correlation of the lower North Atlantic deepwater transport with bottom pressure from Grace at all other latitudes. And the yellow here highlights the 0.7 correlation outline. So this allows us to study the coherence, the latitudinal or meridional coherence of at least an important AMOC component, this lower North Atlantic deepwater, in the Atlantic. And this is work that's ongoing now, and we're hoping to publish something on this soon. If you want to get the data, it's all available online here at our website, grace.jpl.nasa.gov. There's a lot of information on what kind of processing is done and how to read in the data and what it really means. I would suggest, if you're interested in using this data, to use the Global MASCON gridded data. That's our latest and greatest product, and features very good signal-to-noise ratios over the oceans. And if you have any questions, just feel free to reach out to me. There's also a email link on the website. I mentioned the long data record that we have from Grace since 2002, and that Grace is pretty old now. And in fact, we are more than 15 years in orbit, so and probably won't last much longer, maybe another year if everything goes really well. But we have Grace follow-on coming in 2018. So these satellites are now fully built and integrated. They're undergoing testing right now in Munich, and they'll get shipped out here in a few months and then get strapped onto a Falcon 9 rocket, and we will launch from Vandenberg in early 2018 and then continue this data record from Grace. And really want to encourage, if you have any students or if any students are online here, to take a look at this record and exploit it and really use it over the oceans. So just a few takeaway points here. Grace can measure bottom pressures at about 300 kilometer scale. So I should really be more specific here. Bottom pressure variations on monthly time scales. We regularly map global ocean mass changes, and in combination with altimetry and in situ measurements from Argo, we can really infer on monthly timescales ocean warming down to basin scales. And if we look at residuals between altimetry and Argo, we can also learn quite a bit about deep ocean warming. We can support estimates of deep ocean warming. And of course, when we look at dynamics, we can look at the gradients to study transport variations. So that's it for me. If you have any questions, either ask them now or shoot me an email at just my last name, Landerer @jpl.nasa.gov. Unfortunately, I can't stick around all the way to the end of the telecom, but I'm sure you'll have a way of getting in touch with me. Thank you.
Thanks, Felix. Very nice presentation. We do have just a couple questions, if you could take a moment to answer those before you dip off. So Fred Bingham wanted to know that the deep sea level rise inferred in the South Pacific that you pointed to a few slides back, could it be due to the freshening observed there shown in the previous talk?
No, we looked at this in the paper. It's really more consistent with the warming. Dennis also analyzed the transect data. And I think what's happening here dynamically are wind stress changes, and we have convergence. And I think the signal is steric, but mostly thermosteric in origin. And I see Greg had a question too. Are you still getting monthly maps from Grace at present? If so, what fraction of the months are presently mapped? So yeah, at the very beginning, can I go back here to this slide? Mm-hmm. I can't. Right, I showed that our record is starting to get gappy with Grace. That's because of these aging batteries. So here, the last year here that I show on this plot is 2016. We actually just updated the data record, and we have now filled in October, November, December. Although these data maps have higher errors and uncertainties than previous maps, and we're working on the 2017 map. So the record is getting gappy, but we will have some more data, yes.
Great. Thanks, Felix. I appreciate your time today. And as you mentioned, if there's any additional questions for him, feel free to send me an email. If you don't have his, then I will forward his email along. So thank you. And let's move on to Nathalie. Hi, Nathalie.
Can you hear me? Hi.
Yes.
Okay, so I will present the status of the sustained deep ocean observations. I included this haiku from Greg Johnson. I think it illustrates very well the message I'm trying to send, that there are regions of inky darkness where we don't know much about ocean properties and ocean circulation at depths greater than 2,000 meters. So I will start by presenting the science motivation for increasing deep ocean sampling. Sustained EOVs in the deep ocean will rely on programs that are complementary for resolving spatial and temporal resolution of relevant EOVs. The deep ocean observing strategy includes programs that are in place and new technologies. And for this talk, I will focus on Ghost Ship, Oceanside, and Deep Argo, and I will finish with a summary. So the science motivation for increasing deep ocean samplings are to close the budget of heat, fresh water, and steric contribution to sea level change, but also to improve estimations of velocity and transport in the ocean circulation, including the MOC. Recommendations from Ocean Observer 9 included repeat hydrography and mode arrays for coast-to-coast and coast-to-ice transport lines, but also deep moored arrays in region of interbasin exchanges and boundary currents and regions of deep water formation. Recommendations from Oceanobs also included what was called at the time deeper reaching Argo floats, and that was to increase sampling of temperature and salinity in the ocean interior. So the repeat hydrography program is the source of much of what we know about deep ocean properties and circulation. Over 10,000 casts were collected at depth greater than 2,000 meters since 2009, and for comparison, over 1 million were collected from conventional Argo. So clearly the deep ocean is undersampled. The repeat hydrography program provides reference data of temperature salinity, but also BGC variables that are used for other programs, including Argo. The top priority of Ghost Ship is to maintain Ghost Ship lines and collect data at least once per decade. What you see in this map is the Ghost Ship sections schedule for 2012 and 2023. What is missing in here is the sampling at a higher frequency. So, and that's the mission of Oceanside's. Oceanside's mission is to provide high quality continuous data at fixed locations. There's about 200 platforms that are currently active. After 2011, it was decided that Oceanside would make use for increasing deep temperature and salinity and pressure. And there's over 88 sites that are currently active, and Oceanside has a pool of microcats that could instrument 10 to 15 more sites. So going back to the previous slide, so here we go. So you see in this map that there's regions where there's no sampling at frequency higher than once per decade provided by Ghost Ship. and the mission of Deep Argo is to fill this gap. There are 4 Deep Argo float models that were developed. The Deep Ninjas and the Deep Arvors, which sample temperature and salinity to 4,000 meters, and the Deep Apex and the Deep Solos that collect temperature and salinity to 6,000 meters. The CTD, an extended version of the CTD mounted on core Argo floats is used for Deep Ninjas and Deep Arvors. And a new CTD SV61 is used for Deep Solos and Deep Apex for measuring to 6,000 meters. The Argo community envisions an array shown here of 1,228 floats for at 5 degrees spacing. The Deep Argo floats will sample every 15 days. And Argo's community envisions to extend Deep Argo sampling across seasonally ice-covered regions. Deep Argo is currently in its implementation phase. Regional pilot arrays are necessary to demonstrate the technical capability of the CTDs and the Deep Argo floats. Also, the feasibility of deploying and maintaining large-scale arrays, and also to demonstrate the scientific value of systematic Deep Argo observations. There are currently 36 Deep Argo floats that are active in the North Atlantic, Southwest Pacific, and South Australian Basin. The size of the Deep Argo array will double by January 2018. We'll extend the pilot array in the South Australian Basin to the Australian Antarctic Basin. We'll increase the size of all arrays, and then we'll implement a new array in the Brazil Basin. The global implementation of the Deep Argo program could start in 2 to 3 years after assessment of performances of the floats and the CTDs, and also after an increasing support from our regional international partners. So we chose the Southwest Pacific Ocean for Deep Argo pilot array deployment because it has a robust multi-decadal deep warming, as was mentioned in the previous talks. It's also on the pathway of deep water masses. As Greg mentioned, it has a stable temperature-salinity relationship, which is useful for testing of the CTD. There are 11 Deep Solos marked in blue that are currently active and 2 Deep Apex. And we plan to deploy 3 Deep Solos at 32 cells in July and 5 Deep Solos on board the Cara in October. There's additional deployments that are likely for 2018. The panel to the left is showing potential temperature as a function of salinity for all Deep Solo floats that were deployed since January 2016. And the panel to the right is showing potential temperature as a function of salinity from repeat hydrography data of 2009 in the Southwest Pacific pilot array. So if you look at the this panel here, you see a tight relationship between potential temperature and salinity, which is indicative of stable, well-mixed water masses. And by comparison, the Deep Solo data shows a larger scattering and fresher values of the Antarctic bottom waters. I plotted here salinity differences at 0.7 degrees between Deep Solo and reference data. The salinity anomalies are color-coded for all Deep Solo floats active in the pilot array. We see negative values, which indicates a fresh bias of 0.0037, which may be due to an incorrect value of the compressibility of the CDD cell. If we do the same exercise at 2 degrees, we find a smaller fresh bias of 0.0016, which suggests that this fresh bias is pressure dependent. We found a salinity scatter of plus or minus 0.004, which is partly due to random pressure error. The comparisons between CTD 61 data and shipboard CTD data along P15 south from last year showed that the pressure sensor accuracy is about plus or minus 5 decibars, which could generate a salinity error of 0.002 and explain some of this salinity scatter. The variability of the salinity anomalies for each CTD is of 0.001, which is within the accuracy, the target accuracy of the CTD, and indicates that most CTDs are stable. So this slide is an example of the exciting science that can be done by merging deep Argo data with trajectory-based velocity at parking depth from conventional floats. I computed the absolute velocity as 60011 to 604 and 609 to 605 lines, and that's shown here. Negative values are for southward flow, so I found a broad southward flow across those lines with higher velocities of 0.3 to 0.4 centimeters per second between 3,000 and 4,000 meters. And this is in great agreement with results from Wessels et al. From inverse solutions based on WRF's data along PO6. In Susan's result figure here, you see that the gray shaded region here is indicative of a southward flow below 2,000 meters with velocities of 0.3 to 0.4 centimeters per second at the same depth as from the deep solar results. Okay, so we picked also the North Atlantic Ocean because we wanted to look at the internal variability of the ocean properties and circulation of North Atlantic deep waters near formation region and also in the ocean interior. There are currently 4 deep harbors active, 3 from France, shown in yellow, and 1 from Spain, shown in green, 1 deep apex from the UK, and 6 deep solos from SIO. We plan to deploy an additional 17 deep harbor floats in July 2017 in the northern part of the array. Okay, so our final pilot array, as mentioned earlier, we have deep solo floats and 1 deep APAC currently active in the South Australian Basin, and we plan to extend this array to the Australian and Antarctic Basin. So our motivation for this array is to look at the spreading of Antarctic bottom waters from near formation regions into the Pacific and the Indian. This region is also great because it has a lot of sections from the ghost ship, which not only provides reference data but also deployment opportunities. We plan to deploy 5 deep solos in yellow, 3 deep harbors in gray, and 3 deep ninjas shown in blue in January of next year. And we might also do additional deployments along I-9 in 2020 and maybe additional deployments before that. Okay, so to summarize, Ghost Ship, Oceanside, and Deep Argo are complementary programs that are well fitted for observing the deep ocean. The internal to decadal variability of ocean properties and ocean circulation at depths greater than 2,000 meters is not well understood, and we need to increase deep ocean sampling in the ocean interior, but also at ocean boundaries. Thank you.
Thank you, Nathalie, for the nice presentation. Are there any questions coming in from the audience? You can raise your hand or type them in via chat, and it looks like we do have one. Nathalie, Mike Patterson wanted to know, what is the anticipated timing for a global deployment of Deep Argo?
Well, I think our understanding is that it could start in 2 to 3 years from now.
Great, thank you. Okay, if there's no other questions at the moment, we'll move on to our final presentation for the day. Thanks, Nathalie. And up last, but definitely not least, is Charlie Eriksen. Charlie, are you with us?
I am.
Hi.
Can you hear me?
Please feel free. Yeah, you sound great. Get started.
Okay, great. That was a nice talk that we just heard about deep Argo, and I'm going to show some complementary technology for measuring the deep ocean with deep gliders, and they measure more at more deliberate sites and on finer scales, and that is presumably quite interesting for things like western boundary currents and the Antarctic circumpolar current and places like that. So I'm going to show you some of this technology first. This is what deep glider looks like. Let's see if I can get my. There's a picture of it gliding. It's as the specifications. It's under 2 meters long. Any two of us listening can pick one up. They're getting a little heavy, around 75 kilograms. The latest two have been closer to 80 kilograms. They can go to 6 kilometers depth, and they can last, in principle, up to 18 months. We haven't done that yet. We've had one go over 9.5 months. We keep trying to extend that record. In 9 months, the one that we lost at 9 months had used half of its battery power, so it was on track for an 18-month mission before it had some communication difficulties. Well, what's measured on these? There's a CT sensor. It's the same CT sensor that is used. It's a Seabird CT sensor. It doesn't have a model number because it's a specialty implementation of Seabird's technology. It's the same, essentially the same sensor as is on their commercial sensors. And the only difference is this one is free-flowing. It's not pumped. So there's a thermistor, and this is the conductivity tube. So that's mounted in the front. We also have an oxygen sensor and optode. In this picture, the optode is on the back of the instrument. We found, actually, we've moved it to being on the mast so that when the vehicle comes to the surface and the mast is exposed to air, we get an air sample, and that allows us to calibrate the optode and take out drift kinds of things that are well known for optodes now. So that's a big plus. Well, so basically there's a pressure case, there's a forward flooded area and an aft flooded area. Those flooded areas are filled with something we call a compressee. It's something that's quite squishy, has high compressibility, but 5 times the compressibility of seawater to make up for the rather stiff hull, and that so we can tune the whole vehicle to be nearly neutrally compressible, so that we can get it to from the surface to the bottom of the ocean with only something like 50 grams of variation throughout the water column. And what that means is that the electric energy that's in these batteries can go toward running the pump to inflate this swim bladder, and that provides only thrust in effect. So that extends the endurance a lot, and that's the key of getting this long-lived vehicle going. So let's see if I can show the next slide. There we go. So here's a picture of 2 old men putting one in, and you only need a small boat to launch one of these. As I said, any 2 of us can pick one up and move it around. This is what it looks like at the surface. Let's see if I can get the slide to advance. I'm having trouble getting the slide in that. There we go. So that's what it looks like at the surface. Just the antenna is showing. It spends about 10 minutes at the surface maximum, makes a telephone call over Iridium to send all its data in, and receives commands from a base station. So my mouse is having trouble doing these slide advancements. So here's again a picture of it gliding down rather steeply near the surface. It flattens out and shortly after that, and goes at a more gentle angle onto the data that we have. I'm going to show here a picture of 3 long deployments. These were all from Bermuda. There's Bermuda in each slide. We took one and sent it across the Gulf Stream. The dark blue lines are the depth average current, and light blue is the transport across that section. And you can see down the bottom there are the reference areas. So an arrow just that long corresponds to 10 sphere drips. And so if you add this up, you find something like 100 sphere drips or 150 sphere drips or so across the Gulf Stream. I tried to look at how much transport that you could get by, say, going from Bermuda down to the Bahamas, and see how that compared to going across the Gulf Stream. We did it twice, and a couple of months apart. These trips take 80 days, and it ends up that you get rather different transport numbers, that these transports are aliased considerably by barotropic flows. You can see there's a big burst here. This is about apparently 100 sphere drip sort of contribution just from a mesoscale eddy going by and not resolving the eddy very well. So that's the problem of trying to get transport from these guys, but you can make long missions, and you can make a relatively straight trip across the Gulf Stream. So what we do with them in sampling, each dive climb cycle is one of these up-down V's, and if we take a pair of them, say in red, or a pair of successive profiles of dive cycles in green, we can estimate, say, for this red location, from the horizontal differences in density, we can get geostrophic shear. We integrate that vertically to get a relative velocity profile, and then reference it to the depth average current that we get from knowing how fast the vehicle goes through the water, and we can get absolute geostrophic currents based on 2 to 4 density samples at each depth. These are done over, takes about 2 days to go down to 5,000 meters and come back up to the surface. So these are, by their very nature, rather low frequency, in the sense that they could, we can infer geostrophic currents from them. So here's that section across the Gulf Stream. You can see the strong part of the Gulf Stream here, and you can see barotropic tendrils coming down to indicative of barotropic flow, having deep tendrils coming all the way to the sea floor. And we look to see what at the sea surface, how the horizontal velocity that we got there compared to, say, satellite measurement. So we're right under one of the tracks of adjacent satellites, and of course, adjacent satellite goes along that track for a few minutes in the North Atlantic, and then comes back 10 days later and does it again. Whereas the glider takes considerably longer to go across. So in these pictures, the solid lines are portions where the glider was estimating surface velocity, and so there's a big one going across an eddy. The dashed ones are where what you get from the altimeter, and they are close to the same. There's the core of the Gulf Stream itself. We get higher velocities, surface velocities from the deep glider, because we don't do as much smoothing as is done with the altimeter track estimates. But there's over 2 2 meters a second at the surface. So we think that technique works pretty well. Going on to the next slide, here's what we did at Bermuda. We went around a repeat track centered on the BATS site. That's the BATS site. So we went around and around this a number of times, about every 2 weeks for 9 months, and we saw interesting things like the passage of a laboratory sea eddy that came in here. This is oxygen plotted against time. But what I really want to show is the nice thing about being able to do full depth profiles is that we can get full depth profiles of absolute current, and this looks a lot like the first baroclinic mode and the barotropic mode dominate, but there's some other energy in there. By contrast, in vertical displacement, these are plots of vertical displacement inferred from changes in density relative to the long-term mean there, to the record mean, and we were seeing big changes in deep displacement all the way down at 3,000 meters of hundreds of meters. So look at the scale here. This is 200 meters depressed. This is 100 meters elevated. So there are these big things. It doesn't look like it's dominated by the first baroclinic mode. It's actually a number of higher modes seem to be there. So the conventional wisdom that the first baroclinic mode does it all isn't consistent with these pictures. And this is the kind of thing we can see. Now here is some of our latest measurements. We launched a couple of gliders at this location north of the Bahamas. We did this because we weren't able to get permission in time to operate off of offshore of the Bahamas with small boats. So we took a small boat from Florida. We went out 120 miles out to this location, launched gliders. We didn't go as far as we would have liked to. And of course, the first thing that happened was we got caught in a very strong depth average current of the Antilles current coming north of the Bahamas on its way to joining the Florida current to form the Gulf Stream. And this was rather a trick to manage to keep the glider from moving off to the Gulf Stream. We managed to save it, get across the Antilles current, get into an eddy, ride the eddy across, and make it into deep water. And now that the depth average currents are much weaker, the idea was really to get to this area and do back and forth sections along the rapid Mocha line, and that's in support of the effort there to measure the Atlantic meridional overturning circulation. So we have two gliders doing these 125 kilometer sections. I just asked yesterday for one of them to go another 125 kilometers out, so it'll be going back and forth over here starting now. And here's what the section looks like. Here we are going across the Blake Plateau and now going to the southeast to that offshore target, turning westward to here, and then going back to the east. And these are contours of current to the left of the direction of travel of the vehicle. So the colors flip. This is the Antilles current. This is also the Antilles current. And again, there's the Antilles current once again as we go across it. And this is northward current. Down beneath it is the deep western boundary current. As we got offshore, we managed to see this one big stripe of barotropic flow, and that motivated us to want to go further. And of course, one of the things that's critical is being able to do this, do such measurements in a resolving manner. This is a slide that I developed from some code that Dan Rudnick shared with me. It really is gives the point. This is a sampling pattern, a map of the error that you get from getting a daily profile of a glider going across a section 200 kilometers long, turning around and coming back. This is a slow-moving one, only 15 centimeters a second. Gliders themselves can move, say, 25 centimeters a second through the water, but to deal with strong currents, they might make it over the ground only 15 centimeters a second. So that's why I drew this as being slower, and it could go out to 200 kilometers and come back in about 30 days out and back. And if the correlation scales are 25 days of the flow and 25 kilometers, you basically get 20% error just on the edges in the wedges between where the glider went. By contrast, if you had a mooring 50 kilometers out and you had one at the beginning of the section and another one, another 50 kilometers and another 50 kilometers, with the same scales, you get much bigger errors, 60, 70, even 60, 70% error between the moorings. You're basically not taking advantage of the spatial scales and the temporal scales of the flow. If you manage to move a sensor around, that's much more effective than staying put to resolve a section. So basically, that's the kind of strategy that we follow in choosing how we make a section. So in summary, I want to say that these are vehicles that have very high endurance. They can persist in the ocean, take measurements over a long time. They do the full 6 kilometers depth. Right now they're measuring temperature, salinity, and oxygen. There may be some chemical sensors that we can add on board that are electronic and without breaking the power budget. We get absolute geostrophic current and transport. We get near real-time data return. We can launch and recover from small boats, which keeps the cost down. The yearly operational cost is equivalent roughly to the cost of a day of ship time. So you could enhance the sort of sampling that Go Ships has by using these at places that you want to concentrate on boundary currents to resolve them, or you could go all the way across the ocean every year instead of waiting 10 years apart. The drawback is, of course, that you only get a few variables instead of all the measurements that Lynne mentioned that the ships can do at this point. So they're quite effective tools for resolving short, sort of 200-kilometer-ish kinds of sections, and they are boundary current capable and likely also capable of going across the ACC. So we have 1 minute till the hour-and-a-half bell, and we made it. So that's all I have to say. Thank you.
Thank you, Charlie. Another well-done presentation. We do have a question that came in for you, and right before I ask this, if there's any other questions, people may want to go ahead and type those in or raise your hand. We'll take a minute or two to address any final questions. But Charlie, why don't you go ahead and answer this one that Renelis had. She wanted to know, how much time does it take to sample across the Rapid MOCA WBPS line of the moorings? Will you use, or are you using, the shipboard hydrographic data along 26 degrees north for calibration of deep gliders?
The answer to the second question is yes. We are using that for calibration, or to check the calibrations that we have. Let's see, do I have a time here? This whole section went from April, a little over a month to do all of this. Each of these sections, let me go back one more slide here. Each section is taking 6 or 7 days to do, so 6 or 7 days out, 6 or 7 days back. So I think that answers what Renelis was asking. There is a ship out there right now. The moorings are being turned around on Bill Johns and company are out there doing a mooring turnaround cruise, and they've taken a number of CTDs that they've managed to take 2 CTDs during a single deep glider down up profile in the same location. So we have nice calibration data. I have data from previous cruises from a year or so ago, and it looks like our calibrations are within a couple of milledegrees of those. We'll see if what the concurrent measurements see when I get those data from Bill's crews.
Great. And one final question, which I think is a great one to wrap up on for our remaining 3 speakers, which is where do you hope we will see, or where do you hope we will be in terms of deep ocean observations in the next 10 years? So if Charlie or Greg or Nathalie are 3 presenters remaining, if anyone wants to take that on and give their hopes for what we could see happening in the next 10 years, we would love to hear that.
Well, I see that the question from Mike says, do you envision sustained or operational deployments contributing to the global observation system? If yes, where and when to be implemented? Frankly, we can, and it's just a matter of whether the community wants to lend the resources to make that happen. We are on a proposal by proposal basis. This section off of Abaco is supported by NSF, and I would love to enhance that section and work on other sections as well. I don't see any reason that we couldn't. I propose to work in the Labrador Sea, make sections across the Labrador Sea on the AR7 repeat line, and unfortunately that proposal got turned down twice. So we're not looking. That doesn't seem to be competitive at the moment with where NSF wants to spend its money. But we certainly see that that these deep gliders could complement greatly what Deep Argo is doing.
So can I jump in on that question about the next 10 years? I think we would like to see the next Go Ship survey complete and including more biological measurements and providing a baseline still for calibration for Deep Argo, deep gliders. We'd like to see ocean sites expanded into areas where they can measure variance in different regimes of deep temperature and salinity. We'd like to see Deep Argo building out, starting probably from where we're seeing large signals in the southern hemisphere and the North Atlantic, and then building into the North Pacific and North Indian Oceans. We'd like to see deep gliders probably complementing both those all those observing systems in measurements in boundary currents and other critical regions.
Thanks, Greg. Nathalie, anything to add on to final remarks?
No, I think, well, obviously I would love to see the Deep Argo array globally implemented, and I would love to see us reaching our target of 1,228 floats by then.
Great. And Charlie, any final thoughts from you before we end today?
I just hope that that our government sees fit to, our society sees fit to support science in the as it has for the last 50 years. We dearly need it to continue.
Excellent, thank you. I want to give everyone a really big thanks for tuning in today, and an extra warm thanks to all of our presenters, those for contributing to today's webinar, as well as contributing articles to our most recent edition of Variations. I will put this on our website, and you will be able to find it here within this week. So thanks everyone for tuning in, and we hope to see you on the next webinar. Have a great day.